Lissa Productions.
Today we're going to be talking about bipolar junction transistors, or as you might see them written in the literature, BJTs. There are two types of these transistors, and it has to do with the semiconductor structure of them, the PNP and the NPN. And they differ by the direction of this sort of diode symbol on this one leg here. The legs on these, there's three basically inputs to these things. There is a base, which we denote with a B on both of these. So B equals the base. There is a collector, denoted C, and there is an emitter, denoted E. And we're going to be worried about, the one we'll use the most, and what we're worried about is the NPN transistor here. We can go inside and look in this a little bit to see how it's sort of connected. And it really looks sort of like two diodes. There is the base, and then what looks like a diode to the emitter. And similarly, there is what looks like a diode to the collector. And it's possible for current to flow from the collector to the emitter. So this is sort of what we look at in here. And the normal operating state of this transistor requires that the base emitter junction be forward biased and the base collector junction be reverse biased. That sort of says if we're going to apply DC voltages to these, then VB is going to be less than VC to reverse bias that junction, and VB is going to be greater than the emitter voltage here to forward bias that. And in fact, it behaves just like a diode, so if it is forward biased, then we can use our diode approximations, and VB is approximately VE plus one diode drop, or 0.65 volts. So let's look a little more carefully at this here, okay? So we have the NPN transistor. We can now talk about biasing DC voltages, a base voltage, a collector voltage, and an emitter voltage. And these, we said, the collector voltage has to be bigger than the base voltage to reverse bias that, and we forward bias this, and so the base voltage is the emitter voltage plus 0.65 volts. Okay. If we have it biased like this, we can talk then about the currents flowing into and out of the transistor here. So we talk about a collector current flowing into the collector, a base current flowing into the base, and an emitter current flowing out of the transistor. So we have to have the currents flowing in, IB, plus IC has to be the current flowing out, IE. One other thing happens. If we have biased the transistor in this way, then there is a relationship between the base current and the collector current such that the collector current is some approximately constant beta times the base current, where beta is a large number, say on the order of 100 or so. So if we bias it this way, put a tiny current into the base, a big current flows into the collector. And then given by this relation here, IE is then going to be 1 plus beta times the base current. Little current in, big current out if we set the biasing up. We can also talk about a relationship between the collector current and the emitter current. So here we just simply replace the collector current with, replace the base current with, it's 1 plus beta over beta times IC, or if you will, IC is beta over beta plus 1 IE, and that combination is sometimes referred to as alpha. So that is what we talk about a normally biased transistor. If we set these two conditions up, then that condition is satisfied and the beta of the transistor is large, on the order of 100. So let's talk a little bit about what that means for performance. Okay, so we have our properly biased transistor. We know that the collector current is beta times the base current. So we can talk about the IV curve of this transistor. So draw our IV curve here. We normally plot this as the collector current here. And then what we do here is we plot it against the voltage between the collector and the emitter, voltage VCE. And for a given base current, this just says that the collector current is constant. So there's some particular base current. If we took a bigger base current, we'd have an IV curve that looks something like this. It would be bigger, and so forth. So it's a flat IV curve that's basically given by the base voltage. Now you notice I didn't quite draw it over here to the zero axis. What actually happens is there's some turn on the transistor, so there's a curve that kind of goes up and these all connect to it. So it's some low voltage it's turning on. We won't worry about that. We're interested here. There's also another limitation. There is a maximum power that we can push through the transistor before it blows up. It doesn't actually blow up, but you get little smoke coming out of it. And that power curve, the power is VCE times IC. So the power curve, there's a maximum power that looks something like this on here, P max. And these curves kind of go over and hit that curve there, turn up just slightly, and if you cross that curve, the transistor dies. So what we're usually looking at is we're operating in this flat region here, where the transistor behaves very much like a current source, constant current independent of the voltage. So that's the IV curve of a properly biased bipolar junction transistor. Let's now do one more thing with this. We talked about DC voltages biasing the base. We'd also like to add an AC voltage to that. So let's look at what that means. So AC voltage, let's just look at the base here. We can draw our transistor again. We have the DC, V base, V collector, V emitter. And we're going to talk about a total voltage. So let's look at it on the base. V total on the base is going to be the DC level plus some AC signal that we add to this. You can imagine adding some VB of T onto that DC level there. So there's the total voltage at the base. We can do the same thing at the other two. V collector total is VC plus some AC signal added to the collector, and V emitter total is the emitter voltage plus some AC signal added to the emitter. So if we have it properly biased, forward biased diode there, then the base voltage, the total, has to be total emitter voltage plus 0.65 volt from the diode drop. We can now put what we know about the base in. It's a DC level plus an AC. So VB plus VB of T has to be VE plus VE of T plus 0.65 volts. I'm going to now take the DC levels on one side and the AC on the other. So VB minus VE minus 0.65 volts has to be negative VB of T minus VE of T. This is just the diode condition, which we know is true. That means this has to be 0. So this is 0, so it tells us that the base voltage is equal to the AC emitter voltage. So the AC emitter voltage is just a copy of the DC voltage. So that maybe is interesting, maybe is not, but we'll see how to use that as we go along. But basically, right now it looks like a transistor is a fancy way to make a copy of an AC signal. So let's stop there for today.